Hello friends, welcome to my last lecture on solution of first order nonlinear equations. In my previous lecture, we discussed about how to solve first order nonlinear equations which cannot be reduced to any of the four standard forms. The method applied for solving such nonlinear differential equations of first order is Charpit's method. In the Charpit's method, we have seen that if the differential equation is given by f x y z p q equal to 0, then we try to find a relation in the variables x y z and p q equal to 0, which we denote by phi x y z p q equal to 0, such that by the two equations f x y z p q equal to 0 and phi x y z p q equal to 0, we determine the values of p and q, and then we put them in dz equal to p dx plus q dy. If it is integrable, we get the solution, that is the complete integral of the given partial differential equation. So let us assume that the partial differential equation is f x y z p q equal to 0, and there exists a relation in the variables pi x y z p q equal to 0. Then the auxiliary equations we have seen are given by dp over delta f over delta x plus p delta f over delta z, dq over this, and dz over minus p delta f over delta p minus q delta f over delta q, dx over minus delta f over delta p, dy over minus delta f over delta q equal to d phi over 0. Now from these equations we try to find the simplest relation which will give us the value of p and q, and thereby by using the equation f x y z p q equal to 0, we shall be determining the value of the other variable, that is q or p. Now once p and q are known, we shall be able to determine the complete integral. So let us see how we apply this method. So we should consider the simplest relation involving at least one of p or q for phi equal to 0. We will have to look for the simplest relation here involving one of p or q, so that we can determine the values of p and q. So it is easier to determine p and q. Then using dz equal to p dx plus q dy and integrating, we obtain the complete integral. The general and singular integrals are obtained as usual from the complete integral. Let us look at the first partial differential equation of first order, which is nonlinear, z square equal to p q x y. So here we may write this equation as z square minus, so let us say let f x y z p q be equal to z square minus p q x y equal to 0. Then we can find the partial derivatives of f with respect to x, y, p, q and z. So partial derivative with respect to x, let us find first. So this is minus p q y. Partial derivative with respect to y we can find, so which is minus p q x. Now partial derivative with respect to z is 2z. Partial derivative with respect to p comes out to be minus qxy, and lastly partial derivative with respect to q comes out to be minus pxy. So once we have the values of these five partial derivatives of f, we can then write the subsidiary equations. The subsidiary equations are let us write how the subsidiary equations are this one. So dp over fx plus pfz, we can write in short fx plus pfz, and then dq over fy plus qfz, we have then dz over minus pfp minus qfq, and this is equal to dy dx over minus fp equal to dy over minus fq. and which is equal to of course d phi over 0. So, we do not need that. So, let us put the values of the derivatives here, and we will see that what we get is this. So, dp over fx plus pfz, fx is equal to minus pqy. So, we get hence dp over fx, fx is minus pqy plus pfz, pfz is 2zp okay, then dq over fy is equal to minus pqx, and then we have q times fz. So, q times 2zq, okay, then dz divided by minus pfp. So, minus pq minus p into fp. So, pqxy, and then minus qfq will also give you pqxy. So, we get doubled here 2 times, and then we get dx over minus fp. So, we get qxy, and this is equal to dy over minus fq means pxy. Now, from these auxiliary equations or subsidiary equations, we try to find the simplest relation involving one of p or q. Now, here it is if you see these equations directly, we do not find any such relation, but we notice that if we multiply dp by x dp plus p dx, we get minus px qy, and then 2x zp plus p dx. So, pqxy equal to by dq plus q dy. So, by into dq will give you minus pq xy plus 2zqy, and then we have q times dy. So, q times dy means pqxy. So, this pqxy will cancel with this pqxy will cancel with this, and we have x dp plus p dx divided by 2x zp equal to by dq plus q dy divided by 2z qy. Okay, or x dp plus p dx divided by xp equal to by dq plus q dy divided by q. 2z we can cancel. Okay, so now this is this we can write further as or this is d of x into p. The numerator is d of x into p, and then xp equal to d of by q over by q. Now, when we integrate this, this will give you xp ln xp equal to ln x by q plus ln, let us say, b, or we can even take ln a. So, we shall get px equal to aqy. So, we get a relation between P and Q, that is Px equal to AQy. Now let us use that relation and determine the values of P and Q with the help of the given equation. So Z square is PQxy, since Z square is PQ, so let us put the value of Px equal to AQy. So A times Q square by square we have. So if you can put here instead of A square, it will be better. So we will get Z square equal to Px into Qy. Px is A square Qy, so A square Q square by square, and so Z is equal to AQy. Okay, so this means that Q is equal to Z upon Ay. We have got the value of Q and it is Z over Ay. Now from Px equal to A square Qy, now P is equal to A square Qy divided by x. So let us put the value of Q here. So A square by Q is Z over Ay. So Z over, we have A square by Z is Q is Z over Ay into x. Okay, so this will give you, we can cancel this and we can cancel one A, so we get Az divided by x. So we have got the values of both P and Q. Now let us use dz equal to P dx plus Q dy. So P is equal to A square, P is equal to Az divided by x dx, and Q is Z over Ay dy. Okay, now we can divide this equation by Z. So R dz by Z equal to A times dx over x plus dy over Ay. When we integrate this equation, we get ln Z equal to A ln x plus 1 by A ln by plus, let us say, the constant ln b. So this will give you Z equal to x b times x to the power A and by to the power 1 by A, which is the complete integral. So which is the complete integral. We know that the general integral and the singular integral can be obtained from the complete integral. For the general integral, we put b equal to phi a, then differentiate this equation with respect to a, and then eliminate a between the equation which we get from this equation by putting b equal to phi a and the equation which we obtained by differentiating this equation with respect to a. So we know that method, and then for the singular integral we differentiate the complete integral with respect to a and b, and then eliminate a and b between the three equations, that is this one and the two equations which we obtained by differentiating with respect to a and b. So that we can easily do once the complete integral is known. Now if you closely observe this given differential equation, it can be solved by substitution also. We will be able to convert this equation into the equation of the standard form, that is type 1. Let us see, we have alternate method ELITA. So let us notice that Z square is equal to PQ xy, and this can be written as R 1 equal to x into x by z into P and by z into Q. This is also equal to x by z, delta z by delta x, and this is y by z and delta z by delta y. So if we define capital X equal to ln x and capital Y equal to ln y and capital Z equal to ln z, then this equation 1 will become, then 1 becomes 1 equal to delta z by delta x into delta z by delta y. We can see this easily. Okay. So now this, if you regard delta z by delta x, let us say let delta z capital Z by delta capital X be equal to P and delta Z capital over delta X be by be equal to Q, then we get PQ equal to 1 or PQ minus 1 equal to 0. So which is part PDE of type 1. And the complete integral in this case is Z equal to A capital X plus B is equal to 1 over A, so 1 over A by plus some constant B, okay. Or we can say, now let us replace the values of X, Y and Z, so ln Z equal to A ln X plus 1 by A ln Y. Now here I can write ln B, I think it will be better if we write ln B, so ln B we have, and then we have Z equal to B times X to the power A by to the power 1 by A as this is the complete integral. So if we closely observe the given nonlinear first order differential equation by making the substitution x equal to ln x, y equal to ln y, z equal to ln z, we are able to reduce it to the partial differential equation of type 1, and for type 1 partial differential equation we know the complete integral, it is written like this. So we get the complete integral for the given differential equation. Now let us go to another case. So here we notice that the subsidiary equations are such that it is not easy to find the simplest relation involving P and Q. We had to consider P dx plus P dx plus x dp and Q dy plus by dq. So that also we have to do sometimes. Now here we have the partial differential equation P square plus Q square into y equal to Qz. So we here Pfx by Pqz equal to P square plus Q square into y minus Qz equal to 0. We can find the partial derivatives. Partial derivative of f with respect to x is 0 because the right hand side there is no x. Partial derivative of f with respect to y is P square plus Q square. Partial derivative of f with respect to p is 2py. Partial derivative of f with respect to q is 2qy minus z, and the partial derivative of f with respect to z is equal to minus q. So once we have these derivatives, we then can write the subsidiary equations. The subsidiary equation turn out to be dp over minus pq, dq over p square plus q square minus q square, dz over this, dx over this and dy over this. Now we can look at this first relation dp over minus pq equal to dq over p square plus q square minus q square. So this is dp over minus pq equal to dq over p square, dp over minus PQ equal to dq over p square, and from this we can see that dp over dp over minus q equal to dq over p, or we can say p dp plus q dq is equal q dq equal to 0. So we will integrate this, we will get integrating this, we can write this is p square by 2 plus q square by 2 equal to a constant, let us write a square by 2. So that we will have p square plus q square equal to a square, where a is an arbitrary constant, and then the given PDE becomes a square into by equal to qz. So this gives us the value of q equal to a square by divided by z. Q equal to a square by over z, and so p square is equal to a square minus q square gives you a square minus a square by divided by z whole square. So this is a square times z square minus a square by square divided by z square, and this implies p is equal to a times under root z square minus a square by square divided by z. Now p dx dz equal to p dx plus q dy. So let us so this is dz equal to p dx means a under root z square minus a square by square divided by z dx plus q is a square by over z. So z r z dz minus a square by dy divided by under root z square minus a square by square. Okay, so z dz minus a square by dy over under root this equal to a dx. Now it is easy to integrate. So integrating this we get under root z square minus a square by square equal to ax plus some constant b, which implies that z square equal to a square by square plus ax plus b whole square, which involves two arbitrary constants a and b, and so it is the complete integral. Which is the complete. Now we can easily find the general integral and the singular integral from this complete integral. There is another example, px plus qy equal to pq. So here fx by z, pq equal to px plus qy minus pq equal to 0. The auxiliary equations are dp over p equal to dx dq over q equal to dz over this, dx over this, dy over p minus y. Now here it is easy, we can see that there exists a relation between p and q, which is given by the first equation dp over p equal to dq over q. So dp over p, so let us use that relation dp over p equal to dq over q. Then this is ln p, when we integrate ln p plus equal to ln q plus ln a. So this gives p equal to aq. When p is equal to aq, the given equation reduces to the given equation becomes px. Px means aqx plus qy minus PQ equal to 0. So, this will give you Q equal to 0, okay, Q equal to 0 or P is equal to AX plus Y. Now, when let us look at the case Q equal to 0, when Q equal to 0, P is also 0. Okay, Q equal to 0, P equal to 0 means dz equal to 0, because dz equal to P dx. So, Q equal to 0 and P equal to 0 implies dz equal to 0, which implies that z is equal to an arbitrary constant C, where C is a constant. And we see that z equal to C means P is 0, Q is 0, and so it satisfies the given partial differential equation. Now, the other non-trivial solution is obtained when we take P equal to Ax plus Y. So, when P is equal to Ax plus Y, Q will be equal to P upon A. So, Ax plus Y divided by A. Now, dz is equal to P dx plus Q dy. So, P means Ax plus Y dx and Q means Ax plus Y divided by A dy. Okay, so this is equal to Ax dx plus Y dx plus x dy plus Y over A dy, and so we can integrate it easily. So, z is equal to, integrating z equal to A times x square by 2 plus Y dx plus x dy gives you x into y plus y square by 2 into A plus some constant we can take as b. So, z equal to ax square by 2 plus xy plus y square by 2a plus b. This is the complete integral. As usual, the general and singular integrals can be obtained from this complete integral. Now, let us go to the last problem, q equal to minus xp plus p square. So, here we can write f x y z p q as p square minus xp minus q equal to 0. The auxiliary equation, when we find, they come out to be dp over minus p equal to dq over 0, dx over minus 2p plus x, dy over 1, dz over minus 2p square plus xp plus q. Now, here let us consider dp over minus p equal to dq dy over 1. So, because if dq is equal to 0, what we will have here? Dq equal to 0 means q will be some constant, and when q is some constant, p square minus xp minus some constant we shall have. So, dq over it is because we need a relation between p and q. So, what we do is we consider dp over minus p equal to dy over 1, dp over minus p equal to dy over 1. So, this will give you minus ln p when we integrate by plus ln a, or I can write it as ln p equal to minus by plus some constant ln c, let us say, okay, where ln c is minus ln a. So, p is equal to c times e to the power minus by, and once we have p, we can find q from the given equation. So, p q is equal to minus xp plus p square. So, let us put p equal to c e to the power minus by. So, minus xc e to the power minus by plus p square. So, c square e to the power minus 2y. This is the value of q. Okay. Now, dz is equal to p dx plus q dy. So, here what shall we have? P is equal to C e to the power minus y dx, and then we have minus let me repeat this, minus Cx e to the power minus y plus C square e to the power minus 2y. I think we have to write dy everywhere. So, okay, let me write it like this. C, this is P, C e to the power minus by dx plus Q is minus Cx e to the power minus by plus C square e to the power minus 2y dy. Okay, now here we notice that C times e to the power minus by dx, and then minus x times e to the power minus by we have. Okay, we can take this pair, and then we have C square, this is dy also here, and then plus C square e to the power minus 2y dy. Okay, so integrating we get z equal to C x times e to the power minus y from here, and then C square e to the power minus 2y divided by minus 2 plus some constant which we can take as b. So, now this solution involves two arbitrary constants b and c, and so which is the required complete integral. So, once we have complete integral, the general and singular integrals can be obtained from the complete integral. So, we have written z equal to ax e to the power minus y, here in place of a I have written c there. So, and then minus half a square e to the power minus 2y plus b. So, this is the complete integral, and as I said, general integral and the singular integral can be obtained from this complete integral by applying the usual methods. So, with that I would like to conclude this lecture. Thank you very much for your attention.